Good afternoon. Welcome to Transfer Phenomena in Bioprocess Engineering NPTEL course week 5. So today lecture 2 we discuss about the fundamental of Darcy's laws and then packed bed reactor hydrodynamics. So what we are going to learn from this today's session, we will explain the what is Darcy's laws and then what are the assumptions for governing the fluid flow through the porous media. Then determine the permeability, Darcy velocity, then seepage interstitial velocity using the Darcy's law for various engineering system. Describe the construction, then working principle and the design parameters of the packed bed reactor in the bioprocess engineering. And finally, evaluate the influence of how the hydrodynamics, the inside the packed bed reactor, how the hydrodynamics involved here, then pressure drop, there is a pressure drop difference are there or not. Then there is Moss transfers, the residence time on the design and performance of the packed bed reactors. So Darcy's law. So in 1856, the French engineer Henry Darcy, he established the empirical relationship between the flow rate we write Q, then pressure drop we write delta P through sand bed. So the relationship became that known as the Darcy's law, which remains the foundation for the porous media transport. So because of the Darcy's law, he founded the foundation of porous media transport. So during experimentation, what Darcy found out the following observation. The first one is for flow rate. The flow rate Q, that is a proportional to pressure drop delta P. So the flow rate Q is vary linearly with the pressure drop. That's why we are writing the flow rate increases linearly with the pressure difference. Then greater driving force produced for greater flow. Then next is what observation made here, the flow rate increases with the cross sectional area, Q proportional to cross sectional area. The first one is pressure drop, the second one is for cross sectional area. The third one, but here flow rate decreased with the bed length, that's a bed length we write 1 by L. Because longer beds produce a greater hydraulic resistance. Whenever the bed is longer, then always is produce the high hydraulic resistance here. So here quickly here the flow rate, that is a proportional to delta P pressure drop, then same A for Q proportional to A, it's both are linearly varying, and other one is for Q decrease this one, the other two delta P and cross sectional area increases, and then the last one is for bed length get decrease whenever flow rate get increase. So what then observation 4, he found that the flow rate depends strongly on the porous material. So what is porous material? The fine sand normally much greater resistance than the coarse sand. So this leads the concept of the permeability. The permeability, why? Because of that the permeability we introduce here. So the another one is for Q, more viscous fluids goes more slowly. So Q 1 by of mu is the viscosity. So here if you combine all, we have 4 effect is there. One is the area, that is linearly get increases, then pressure drop also get increases if whenever the flow rate get increases, then mu and L, that is the viscous and then length both get decreases. So you want a Q equal to A delta P by mu L, you want to remove the proportionality constant. Of course we have to introduce some new proportionality constant that we called as a K. So we can write Q equal to Ka delta P by mu L. So what is K here? The K here intrinsic permeability. So this is called Darcy's law. We called as a Darcy's law. So the Darcy law mainly states that the fluid flow through a porous medium is directly proportional to the pressure drop, that's a pressure gradient, and permeability, that's we write K, then inversely proportional to viscosity by mu. Of course, L also there. So unlike normal pipe flow, the fluid velocity inside the pore is, we cannot calculate directly here. So what we have to do here, instead of the average discharge over the entire cross section is considered here. So the average velocity called as a Darcy's velocity. So what are the assumption here for Darcy's law here? The one is a steady flow, because not an unsteady flow, is a steady flow. Steady flow always the time is independent, the time 0. There is no accumulation. So that we called as a steady flow. Then the single phase flow, it not like multi-phase flow. So multi-phase flow like gas, liquid, solid phase, so many flow there, phases there, but we consider that it's a single phase flow. Then it's a laminar flow and incompressible here. So compressible normally gas, here we always use the liquid, this one, and it's a laminar flow. The Reynolds number should be a less than some values. That's called a laminar flow. Laminar flow we write the dV rho by mu, it's the Reynolds number. So it's always laminar flow, the flow is not a turbulent flow. Then the porous medium is a homogeneous porous medium, then isotropic medium. The viscosity throughout the problem constant, not like varying, just like that. Then the permeability also. There is no slip condition, and then negligible inertial force. Inertial force we have to negligible, then because it's a laminar flow, whenever laminar flow dominates, then the viscous force mu always dominate. Whenever mu high, then the Reynolds number goes low, then we call it as a laminar flow. Whenever this viscous force, viscous here negligible inertial force, this is a inertial force. The we called inertial force, it's a inertial force very high, then Reynolds number automatically very high. So the negligible body forces, these are the assumption for Darcy's law. So what are the assumption here? First, steady flow, that's a independent of time, time t equal to 0, single phase, not a multi-phase flow. So laminar, then incompressible fluid, there is a homogeneous porous medium, the homogeneous, then constant viscosity, no slip condition, inertial force is negligible. So the Darcy's law here, that's a porous media, the packet here, and we called as the area A, and the length is L, but the height of the we called as a delta H. The homogeneous, the porous medium, the length L, we write L here, then the cross sectional area A. So the fluid enters at a pressure P1, is entering as a P1 and exit as a P2, entering in P1 and exit as a P2. The fluid moves only x direction. So there is a y, z, 3-dimensional, but here we are solving as a only one direction. We are also assuming only one direction, x direction. So steady flow, the what we already discussed, the dou by dou t 0. Here density is constant. Incompressible flow, most of the problem, the density is a constant. Then this is a Newtonian fluid. So tau equal to mu of this one. So n equal to 1. It's a Newton's law. Newtonian fluid, non-Newtonian fluids, n greater than 1, less than 1. We discussed thoroughly the previous session. So there is a laminar flow. We assume laminar flow less than 10. Then the porous media homogeneous, isotropic medium. The permeability and viscosity throughout the problem constant. There is no slip condition, and this flow is called fully developed flow. These are the assumptions for Darcy's law. Then only we can solve it. So here, instead of analyzing each and every pore, we will select the representative volume of large, then we will make average pore geometry, then we can compare with the entire bed. So here the pressure force at inlet we called as a P1A, pressure force at inlet. Then pressure force at outlet we write a P2A. So what is the net pressure force here? The pressure difference here P1 minus P2 of A, P1 minus P2 A, that's the pressure difference here. So then viscous drag by solid matrix we called as the FD, we write FD. So now we have to write the force balance. What is the force balance here? We assume steady flow, since the flow is steady, then Newton's second law sigma force equal to 0. So there is a P into A and FD is a drag, viscous drag force. So then FD equal to, we can write P1 minus of P2 into A. So then we assume that this is under creeping flow, the drag is proportional to the velocity. The FD is proportional to the velocity u. So then introducing the permeability here. So FD equal to the mu, then A is the cross-sectional area, then u is the velocity L by K. So now we have to assume we substituted both balance are same, then P1 minus P2 of A here and other one is here, then after cancel that one, then we will get P1 minus, that P1 minus P2 is the pressure drop. The pressure drop delta P, we can write delta P. Delta P equal to mu of this one. So you take u that side, that's a velocity. Velocity we can write K by mu of P1 minus P2 by L. So the P1, P2 what we can write? We can write always delta P. If you make a dP by delta P by this we can write delta X, because you want in terms of pressure gradient, we should know what is the difference between pressure difference and pressure gradient. Pressure difference we write always P2 minus P1, but if I talk about gradient and with respect to the position, so delta X, so this we call as a pressure gradient. Pressure difference only P2 minus P1. So take limit this one, then we get the dP by dx. So once a dP by dx, then finally the value of u we can get, this is a one dimensional y, one dimensional only x we are discussing. We are not discussing y, z this point, only discussing here x. So this is a one dimensional and differential form. Why? Because the dP by dx is a differential form of Darcy's law. So what about negative sign? The negative sign indicates, because there is a negative sign here, u equal to minus of this one, it indicates pressure decrease along the flow direction. So pressure decrease along the flow direction. Whenever pressure this one, it's a decrease the flow direction, then the fluid always moves from higher pressure towards to the lower pressure. That's the meaning of negative sign indicates. Hence velocity is the opposite to the pressure gradient. So if you want to validate the Darcy's law, then the applicable for Reynolds number, it should be a 1 to 10. Then this is a single phase flow, what we discussed already. It's a Newtonian fluid, but normal process we never get a single phase, it always get a heterogeneous phase. So Newtonian fluid, then rigid porous matrix, inertial force is negligible, because Reynolds number we discussed here, dV rho by mu, inertial force negligible, then only Reynolds number become as a 1 to 10. If inertial force that dominate, then we cannot solve that one. So whenever the higher Reynolds number, inertial affects the main effect here, then we have to use for Ergun equation to solve the problem. So what are the key takeaway here? For so far we discussed here, the Darcy's law derived from the experimental observation and macroscopic force balance. Then we discussed the pressure gradient is the one of the driving force for the flow through the porous media. And then permeability here to characterize the and which porous material transmits the fluid. Then we discussed the Darcy velocity, then sometimes we called as a superficial velocity, apparent velocity. So it gives for actual pore velocity, is higher because the fluid flow only through the void space, because whatever the flow only in the void space happening. So Darcy's law valid only for laminar, then creeping flow. Creeping flow also, the viscous force is a dominant force. That's called viscous, this one. Whenever the flow rate is very high, then automatically we already discussed inertial effect become very, very significant. So we should use a Ergun equation. So we discussed some 2 to 3 problems. Basic problem here, a cylindrical core sample obtained, the porous formation of the length L is 8 centimeter. So we have to solve in terms of SI units. Then diameter also there. Then water, the temperature of this one 20.2 degrees Celsius. It flow through core under pressure difference. That's a 1 atmospheric pressure. Then we convert it as a in terms of Pascal. Then there is a volumetric fluid is there. Q value is the convert in terms of meter cube per second. Then the viscosity, of course we know viscosity, since it's a centipoise, we have to convert in terms of Pascal per second. So everything we done. What they are asking? They are asking the permeability of the porous medium in meter square and also in Darcy unit. They are asking both sides. One is a meter square, then Darcy units. So cross sectional area, of course we know A equal to pi d square by 4. So from there we get the cross sectional area. So then cross sectional area, then this is a volumetric flow rate Q equal to our Darcy's law. We know the value of each and every value. We know Q, volumetric flow rate. Then viscosity, we know that in previous problem. Length is also we know, length is here. Then area, we know that one. Then pressure difference, that's a 1 atmospheric pressure. Then we get the value of K. The K is a, we get the value of K, that's a Darcy's law, that one. So now we have to convert in terms of 1 Darcy equal to in terms of meter square. This is a standard unit here. So what value we got already, you convert in terms of Darcy. So then finally we got K equal to this much Darcy here, and now the final problem they ask in terms of meter square and otherwise Darcy. So the interpretation here, it's approximately 6.7 Darcy. It's a highly permeable porous medium. And then such a material always allow the fluid flow to flow easily because of permeable, the highly porous medium, and relatively small pressure drops. Reservoir rocks, packed bed with the coarse particles and highly porous filters, media, all in this type of range, in this range. The problem 2, there is a water at 24 degrees Celsius flowing by gravity through a filter bed, small particles having an equivalent diameter is the 0.06 meter. The diameter here 0.006 meter. The void fraction here, the void fraction is porosity 0.42. Then the bed depth also given, and then water head also there. Properties of water, density we know, viscosity we know, then acceleration also we know, but they are asking determine the superficial velocity, determine the u, the superficial velocity of through the bed. And then delta P, we know that pressure drop, the delta P equal to rho g h, and get the value of pressure, this one. And then the Koenig-Korman equation, this is a K equal to, we can write always, so epsilon already, the porosity value is already given, then the diameter of particle also there, from there we get the K value. So we can get directly what is the K value in the sphere particles. Where they discuss the first principle, the sphere particle here. So then finally the velocity, we can get velocity here, you substitute all the values and get the value of velocity. So from this interpretation here, the pressure driving the flow is generated solely by the hydrostatic head and water above the bed. So whenever the porosity very high or large particle diameter, it increases the permeability. And then finally we got the value of the superficial velocity. These are the interpretation for here, and finally the finer particle always reduce the permeability. It gives result in the lower flow rate and higher pressure drop. These are the interpretation for this one. So then another problem, the example 3, flow through the aquifer, the Darcy velocity and then seepage velocity. So, here the hydraulic conductivity values, K value is also given, that is a 2.5 into 10 power minus 4 meter per second. Then the difference in the hydraulic head also there, that is a delta H value 10 meter. Then the distance between the wall, that is a length equal to 100 meter. Then the effective porosity value also there, epsilon value 0.25. What they are asking, determine the hydraulic gradient, wherever the gradient, already we discussed pressure gradient, this one, same way they are asking hydraulic gradient. Then they are asking the Darcy or superficial velocity. The third point is determine the interstitial velocity or seepage velocity in the pore. We will discuss one by one how to call first hydraulic gradient. So, the hydraulic conductivity value, K value, hydraulic conductivity, K value already given. This value is the 2 point is this one. Of course, the head difference also already the problem given. The length of this also there, then porosity is also there. So, we have to calculate the hydraulic gradient. What is hydraulic gradient here? I equal to delta H by L. The delta H is the 10 already there, 10 meters, then L is the 100 meter. So, we got the value of the hydraulic gradient, that is called I. Hydraulic gradient is the 0.10. So, from this interpretation, hydraulic gradient is 0.10. What do you mean indicate that one? The hydraulic gradient decreases by 0.1 meter per meter of flow length. So, this pressure, that means that the head difference is the driving force for fluid movement through the porous medium. So, the second part, then we have to find the Darcy velocity, that is called the superficial velocity. We write Vd equal to Ki. So, K we know, I also the previous we found that one. So, get the value of Vd, that is a Darcy, V is a Darcy superficial velocity. So, 2.5 into 10 power minus 5 meter per second. So, what Darcy velocity or sometimes we call the superficial velocity, it assumes the entire cross sectional area available for the flow. That means all the entire cross sectional area available for the flow. In reality, the fluid flow only through the pore spaces only, not like entire that one. So, then finally, we have to find the actual, what is the actual for the seepage velocity. So, the pore velocity normally related to Vs equal to Vd by epsilon. So, the Vs is the seepage velocity or pore velocity. So, then from there because porosity value we know and Vd Darcy velocity we know, then finally we are able to find Vs, that we call as a pore velocity or seepage velocity. So, pore velocity done, Darcy velocity from previous this one, then hydraulic gradient also done. So far we discussed, so how to find the Darcy velocities, then pore velocity this one. Now we will discuss about the packed bed reactor, general discussion we will do now. The packed bed reactor here, why the packed bed reactor is a fixed bed, one is a fluidized bed reactor, another is a packed bed reactor. So, the packed fixed bed continuous reactor in which the immobilized enzyme or microbial cell, whatever you take, or retained within the stationary fed, you assume like this. So, inside you pack the material, then whatever packing material inside. So, that is only we are telling that one, immobilized enzymes or microbial cell with the stationary fed. This is the stationary, is not moving bed here. So, while the nutrient or substrate solution continuously flows, the flows here and we will get a product outside. Flow through the void space, there is a lot of void space there, through that only the flow is always happening here. The void space between the two particle, the void space there, through that one is moved here. So, unlike stirred tank reactor, the catalyst remain stationary and only will use for the fluid phase moves through the packed bed here. So, what are the application here? It is a immobilized enzyme reactor we can use here, or wherever wastewater treatment, the packed bed is one of the best for here. Adsorption, biosorption, many problems we always use a wastewater treatment. Sometimes the pharmaceutical manufacturing you want to do, the packed bed reactor is one of the best reactor for this one, or fine chemical synthesis also we can use for the packed bed reactor. So, how to construct the packed bed reactor? So, what are the major components here? And this is a packed bed, you can see here lot of particles are just loaded here. It is a packing material, we call the packing material, and then the one side aeration, and other is a feed inlet, and then feed medium we have to add here, then it goes to this is the outlet of this one. So, there is a temperature control, we have to control temperature control, because since we are dealing with the microorganism, the temperature control is very important. So, the construction of packed bed reactor, the major component here, the packed bed reactor consists of cylindrical reactor vessel, the first point, then packed catalyst particles, there is a particles are there, it is a packed catalyst particle. Then the feed distributor is here, because you cannot pass all, and there is a distributor is there. So, we call as a feed, this is a feed distributor here. Then the support screens of course we need, then the finally liquid outlet. Sometimes what they do, the same packed bed reactor, the recycle also there, it's completely recycle loop is there, that's sometimes optional, but when you want to get the increase the efficiency, and we have to use for the recycle that one. Then another is the external aeration vessel, if it's aerobic, and definitely we have to use for external aeration vessel, if it anaerobic then no need. So, the packing material, what are the packing material we will use here? It carrier material includes, there is a natural and synthetic. So, natural alginate beads, then agar, chitosan, all will use for this one. What are the synthetic here? The synthetic material, packing material, polyacrylamide, then polyurethane foam, ceramic beads, then glass beads. So, all we can use. So, glass beads also we can use, ceramic beads also we can use, and for natural alginate beads we can use. So, these are the how you have to packed bed reactor you have to construct here. So, what are the design feature here? And it should a uniform packing, and it should have larger void fraction. The void fraction should be a large. The porosity should be a high, then only we can use that one, and then high mechanical strength, then uniform liquid distribution, because the distribution uniform, otherwise it goes like lot of channeling, everything will be there. Then the low pressure drop, the pressure drop should be a low, if it very high then we cannot use this one. So, what are the design parameters? If you want to do any packed bed or fluidized bed or any type of reactors, we have to design the parameters or design the variables. So, what are the variables here? The variable first starts with the bed height, that is the one variable, then the particle diameter, that we write a dp diameter, then bed porosity epsilon, that is very important. Then flow rate we write q, always we write a flow rate, then residence time, because how much time the whatever this wastewater whatever staying inside the packed bed reactor, then we call as the residence time, so that we will get a good efficiency of the process. So, these are the important parameters for important variable here. So, what are the working principle here? The step 1, the fresh substrate, see here, and this fresh substrate enter the reactor, it goes to reactor, and how you go it through the void space, there is a particle, through void space only this all move. Then one substrate diffused to the catalyst, because this is a catalyst particle loaded here. So, whenever it enters catalyst, the diffuses, of course some reaction occurs, that is the reaction. Once the reaction done, then the product definitely should come out, the product diffuse back and again come out. So, then product what happened? Product exit the reactors. So, these are the working principle how the start step 1 to step 6. So, the overall reactor performance depends on the mass transfer coefficient, we write KL, mass transfer coefficient, then internal diffusion coefficient is there, D, we call it D, and then reaction kinetics, of course that is very important here. Then how much time the vessel, the whatever this one staying inside the reactor, that we called as the residence time. So, here what is the example here? Immobilized glucose isomerase converts glucose into fructose. So fructose during the whenever the continuous passage through the packed bed column. This is the best example for the packed bed column. So what are the advantage of packed bed here? It's a high catalyst loading because the large amount of catalyst what we can do, we can load it here per unit reactor volume. The conversion is high conversion because you stay long time, the long resistance time, definitely it improve the substrate utilization. Whatever substrates inside, you try to utilize more because of long resistance time. And it's a continuous production, it's not like batch production. You pass through this one and we always get the other side. That is suitable for industrial scale production. So then low mechanical damage because we are not using any impeller inside. There is no impeller. If there is no impeller, then the shear stress is a very, very minimum and we are not using impeller. So then ideal for the immobilized enzyme here. We can use for whenever the immobilized enzyme, this is the best for this one, the packed bed reactor. So what is the catalyst reusability here? Because inside we are loading the biocatalyst, it remains inside the reactor. We can always reuse that one and repeated use, and if you reuse repeated, then it's reduce the operating cost. Finally, the operating cost get decreases here. So what are the limitation of packed bed reactor? So far we discussed the previous one, advantage we discussed. Now what are the limitation for packed bed reactor? So what the limitation here, the first point is the pressure drop. Wherever the pressure loss increases, the pressure loss, that is a delta P, increases with the bed height, then flow rate, then small particle size. So the pressure loss increases with the bed height, then flow rate, then small particle size. So sometimes what will happen when you pass the whatever the solution inside, it never get uniform distribution and it goes somewhere the channeling, it like occurs channeling. So the liquid follows preferentially some pathway and whatever you are passing, it goes only here and there is no other side completely remain unused. Some catalyst is the remain unused here. Then clogging, because of accumulation of biomass, then it definitely precipitate and it reduce the permeability. So then what is the gas accumulation here? The gas accumulation, the CO2 bubbles inside, CO2 bubbles become trapped inside the bed. So example, there is a gas, it produces CO2, then it fits inside, then it's very difficult for this one. So definitely the gas flow is gas inside more and then it gives a mole distribution, not properly that one, it definitely affect the mass transfer. The mass transfer definitely get the reduce that one. So what is the diffusion limitation here? The larger particle always its results longer diffusion path, but the lower effectiveness factors. So that is the main thing, the diffusion limitation here. The mechanical compression, if it's soft particle may always deform, then the bed void always the fraction always decreases, and of course the pressure drop delta P is the increases here. So what is the key takeaway here? We discussed it today. The packed bed reactor provides continuous operation and high catalyst loading, and it's efficient for biocatalyst reuse, and it's definitely making the widely applicable for immobilized enzyme reactor. Whenever if you use immobilized enzyme reactor, it's very, very useful, and we use for wastewater treatment, then the biochemical manufacturing also. For successful packed bed reactor design, it requires balancing permeability, because the permeability is very important, and then the pressure drop also important, and then flow distribution, of course the mass transfers and the diffusion, resistance time and catalyst utilization, all to achieve a, if you want, optimal reactor performance. So we have to adjust all the variable, then only we can get the optimal reactor performance. Thank you.